Here's something that should bother you. Everything you've ever seen, every star, every planet, every galaxy, every atom in your body makes up less than 5% of the universe. The other 95%? We have no idea what it is. We can't see it, we can't touch it, we can't detect it with any instrument we've ever built. But we know it's there. And that's the thing that keeps physicists staring at the ceiling at 3 a.m. This is the story of dark matter, the invisible scaffolding of reality, and the greatest unsolved mystery in all of science. Let's go back to the 1970s. An astronomer named Vera Rubin is studying spiral galaxies, the kind that look like cosmic pinwheels spinning through space. She's measuring how fast stars orbit around the center of their galaxy. And based on everything we know about gravity, the math is simple. Stars on the outer edge of a galaxy should orbit slower than stars near the center. Just like the outer planets in our solar system move slower than the inner ones. Mercury screams around the sun, Neptune creeps. Same principle should apply to galaxies. But Vera Rubin found something deeply wrong. The stars on the outer edges of galaxies, they were moving just as fast, sometimes faster, than the stars near the center. That's impossible. Unless there's way more mass out there than we can see. Something invisible, something massive, wrapped around every galaxy like a giant invisible halo. She called it missing mass. We now call it dark matter. And here's what makes it even more unsettling. Rubin wasn't the first to notice something was off. Back in 1933, a Swiss astronomer named Fritz Zwicky looked at a cluster of galaxies and did the math. The galaxies were moving too fast to stay together. They should have flown apart long ago. Something was holding them in. He estimated the cluster needed about 400 times more mass than what was visible. Nobody took him seriously for decades. Vera Rubin proved he was right. Now, at this point you might be thinking, okay, maybe their math was just wrong. Maybe we're missing something in our theory of gravity. Fair. Scientists thought the same thing. But dark matter isn't just one piece of evidence. It's a mountain of completely independent observations that all point to the same conclusion. Gravitational lensing. Einstein showed us that mass bends light. When we look at distant galaxies, we sometimes see them stretched and warped, like looking through a funhouse mirror. That warping tells us exactly how much mass is between us and that galaxy. And again, there's far more mass doing the bending than we can actually see. The bullet cluster. This is the smoking gun. Two galaxy clusters collided, one of the most violent events in the universe. The hot gas from each cluster, the stuff we can see, slowed down and got stuck in the middle from electromagnetic friction. But the dark matter? It passed right through, like the clusters were ghosts to each other. We can map exactly where the dark matter went using gravitational lensing. It's separated cleanly from the visible matter. That's not a math error. That's behavior. That's dark matter doing something physically distinct from normal matter. The cosmic microwave background. The faint afterglow of the Big Bang is imprinted with tiny temperature fluctuations, ripples from when the universe was a baby. When cosmologists model these ripples, they only work if dark matter exists in exactly the proportions we've calculated. Remove it from the model, and the whole picture falls apart. 3 completely different types of observations. Same answer every time. There's something out there, we just can't see it. Okay, so we know dark matter exists. But what is it? Honest answer, we don't know. But let's walk through the main suspects. WIMPs, weakly interacting massive particles. For decades, this was the favorite. The idea is that dark matter is made of heavy particles that barely interact with normal matter. They pass through everything, like it's not even there. We'd be swimming through billions of WIMPs every second and never feel a thing. We built massive detectors buried miles underground to shield them from cosmic noise, filled with liquid xenon, cooled to near absolute zero, waiting for a single WIMP to bump into a single atom. We've been waiting for over 30 years. Nothing. Axions, a much lighter candidate, originally proposed to solve a completely different problem in physics. And then someone realized, hey, this particle would also make a great dark matter candidate. Several experiments are hunting for axions right now, including one that uses a powerful magnetic field to try to convert them into detectable photons. Still nothing confirmed. Primordial black holes. What if dark matter isn't a new particle at all? What if it's just tiny black holes formed in the first seconds after the Big Bang, before any stars existed? These would be invisible, they'd have mass, they'd clump around galaxies exactly like dark matter does. When LIGO first detected gravitational waves from merging black holes in 2015, some physicists got very excited. The masses were in a range that matched primordial black holes perfectly. But follow-up observations have largely ruled them out as the main component of dark matter. Could they be part of it? Maybe. And then there's the wild card, modified gravity. What if dark matter doesn't exist at all, and our theory of gravity is just wrong on galactic scales? There are serious physicists who believe this. It's called MOND, modified Newtonian dynamics, and it can explain galactic rotation curves surprisingly well. But it completely falls apart with the bullet cluster, and it can't explain the CMB data, so we're stuck. Every candidate has problems. Every experiment has come up empty. Here's the thing. Dark matter isn't just some abstract puzzle for physicists to argue about. It shaped everything. In the early universe, before stars and galaxies existed, dark matter was the gravitational skeleton. It clumped first, and normal matter, hydrogen and helium gas, fell into those dark matter clumps under gravity. That's what formed the first galaxies. Dark matter is the reason structure exists in the universe at all. Without it, the universe would be a featureless soup of gas. No galaxies, no stars, no planets, no you. Dark matter didn't just participate in the history of the universe, it wrote it. And if we could figure out what it is, if we could finally detect it, hold it, understand it, that would be one of the most profound discoveries in the history of science. It would rewrite physics. It would tell us something fundamental about what reality is made of at the deepest level. So, where does that leave us? We know dark matter is real. We know roughly how much of it there is. We know how it behaves gravitationally. We know it's not any particle we've discovered before. And that's it. After nearly 90 years of looking, that's genuinely it. There's something deeply humbling about that. We live in an era of smartphones, AI, gene editing, space telescopes that can see the first galaxies that ever formed, and the most fundamental question about what the universe is made of remains completely open. The universe is telling us something, we just haven't figured out how to listen yet. But here's what I find weirdly comforting. The fact that 95% of reality is still a mystery doesn't make the 5% we understand less incredible. It just means the story isn't over. In fact, we're still in the first chapter. If you want to go deeper on the cosmic mystery next door, dark energy, which is somehow even stranger, let me know in the comments. And if this blew your mind even a little bit, the subscribe button is right there. It costs nothing, and it means I can keep making videos like this.